Hi, thank you so much for joining us this morning for a really exciting talk on AI agents and frameworks. Today, we're joined by Harrison Chase, who's the co-founder and CEO of LangChain, which, as many know, is a popular framework for working with LLMs and AI agents. This is a framework and a company that Harrison launched in 2022. And since that time, Harrison's continued to build LangChain and to develop it into the robust ecosystem that surrounds the company today, with support for building, debugging, monitoring, and evaluating agents, among many other capabilities. And I think, Harrison, you're going to talk to us about a number of capabilities across the LangChain ecosystem today. Is that right?
Yeah, gonna talk about a bunch of fun stuff.
Excellent. Okay, well, we'll hand it over to you, and we'll follow up with questions at the end.
Awesome. Let me go ahead and share my screen. So I want to talk about a number of things today. I think the overarching theme is basically building reliable agents, kind of like yeah, building reliable agents. And I think there's actually a lot of different considerations that go in here. Um, I think building prototypes of agents is easy. Getting something that can be used reliably by folks is a lot harder. And I think there's a bunch of factors that go into it. And maybe just to even kind of like you know, set expectations a little bit in terms of like where we think things are headed. We think things are headed to a place where there's a bunch of agents doing a bunch of different things, like vertically focused, kind of like um, each with their own specific kind of like responsibilities that they're responsible for. And we've seen a lot of these agents, or a lot of these agents attempted to be launched over the past year, 2 years, and some of them have succeeded, some of them have failed. And so I think as a starting point, it's interesting to think about why some of these agents have succeeded, and why some have failed, and what common patterns are, and what we can learn for building, agents that do work in the future. And a lot of these thoughts are in conjunction with Asaf, who's the head of AI at Monday.com, and also the maintainer of GPT Researcher, which is an awesome open source project for research built on top of some of our technology. And so I've chatted with him about some of these stuff, and I think the like why do agents work? Just thinking from first principles, like one, like they work more if the value they provide when they're right is high. Um, the probability that they're right is high, and then the cost, if it's wrong, is low. So if you have something where it's likely it will work, if it works, it provides a lot of value, and if it doesn't work, it's okay, then that's an agent that a bunch of people will use. And so I think as you think about, as we think about kind of like building agents that people will use and are reliable, um, it's interesting to think about these three different axes, and how we can kind of like move the needle on each one. And why am I starting from this rather than talking about like some of our technology? I think it's really like the core fundamental things we think as a company, and I think most people in the industry would agree with this, are that LLMs are great. They're really powerful. They're gonna like transform how a lot of applications are built, but it's still really early on. And so a key thing that we try to do is basically figure out what the agents of the future look like. And because that'll shape the technology that's kind of needed for them. And so if we think these three things will kind of determine what the agents of the future look like, then we should try to understand them more. So you can wrap all of these three things up and put them in a nice, like, fun equation. And then, like, if that equation is greater than the cost of building it, that's like when you'll build some agents. And so how can we build agents that score higher on this formula, that move the needle of these three things in the right direction, that increase this, and decrease this? How can we do that? Um, let's start about with thinking about like the value if something is right. Um, I think so one answer is choose kind of like more valuable applications. This sounds a little flippant, but it's not. Like, if you look at like two of the most popular talks from, this is from Interrupt, our first user conference that we did this past year. Two of the most popular ones were one from Harvey, which is in the legal domain, and one from JPMC, which is in the financial space. And both of them are building agents that really, that are in these like high impact, high value spaces. And so this is an example of kind of like focusing on spaces where the value, if you do things right, is just higher. Now another aspect of this is even within this space, you can do greater amounts of things. So what I mean by that is if folks are familiar with kind of like RAG, which is retrieval augmented generation, so it's like question answering. This is what folks were building kind of like um a year or 2 years ago, a bunch of chatbots over documents internally. And so the time that the chatbot would take to respond was, usually slower than this, or yeah, faster than this actually, like 1 second, 2 seconds, but it was a very short amount of time. And that's great because you can have a conversation. But the downside of that is that it's not actually doing like that much work under the hood. Like it's looking up some documents, usually doing just one search and then responding with an answer. And recently we've seen a trend towards deep research style things. So if you use deep research by Perplexity or OpenAI or Claude or something like that, they'll run for like 5, 10, 20 minutes even. And this is an example of basically the paradigm shifting to a place where agents are doing more work than before. They're not just doing like a single search and then responding with an answer. They're doing a bunch of deep research. And you can see the same thing in coding. So coding, I mean, even before Cursor, there was the autocomplete stuff, like fraction of a second. Then you get Cursor with the chat bar, and you're chatting with it, and maybe it takes 30 seconds to do something. And now we have Claude Code, another kind of like of these async coding agents that you can kick off in the background and they can run for minutes, even hours. And so I think this is another example of basically the types of problems that folks are building agents towards are the things that can do bigger periods of work, and that generally kind of like corresponds to the amount that the agent can run for by itself. So they're generally asking agents to do kind of like longer and longer things. Probability of success. How do we increase the probability of success of an agent? So the what are like why might an agent not uh uh have a high probability of success? One of the problems is they're not reliable enough. You can't control kind of like what's going on in the agent. There's this great term that has come out recently called context engineering, which basically describes like bringing the right context to an LLM. Why is this important? When LLMs mess up, when they usually mess up because they don't have the right context. They also could mess up because the LLMs aren't good enough. Those are kind of like the two reasons. Either they're not good enough or they don't have the right context. And I would argue most of the time they mess up because they don't have the right context. And oftentimes they don't have the right context because as a developer, you can't control the context that is being passed to them kind of like well enough. Um, and so a solution to this is to make parts of your agent deterministic, because then you can control in more detail, kind of like what's getting passed to the agent, what it sees in terms of context. And so what we often see is that a lot of the agents that go into production are not fully autonomous, and they're not like just deterministic workflows, because this would just be like normal code. They're kind of somewhere in the middle. They have some parts that are deterministic, and then they have some parts that are more kind of like autonomous and switching between things. And so this is kind of like, this a spectrum from workflows to agents, where agents you have kind of like really high agency but low predictability, and workflows you have really high predictability but low agency. And the key is being on somewhere on the spectrum, and where you want to be on that spectrum totally depends on the application that you're building. And so one way that we like to think about this, and I will talk about more about this later, is modeling agents as graphs, basically. And the reason this is useful is because some parts of these graphs can have some non-deterministic aspects to it. So from here, you can see that this node here, that after this write assistant node executes, it can either go to this node, it can go to this node, or it can go to this node. And there can be loops in here. This can be a loop, or there can be deterministic things. Like after you go to this node, you always go to this node. And so I think modeling agents as graphs provides a nice mental model for thinking about these things as a combination of deterministic and non-deterministic. Another more subtle thing is that, when when agents don't have a high probability of success, why don't they have a high probability of success? Part of the reason might just be they're really high perceived error bars for the agent. People might not understand how it actually succeeds or when it succeeds, or maybe it succeeds a lot on some types of questions but not so much on other types of questions. And so there's all of this like uncertainty around how well agents actually do, because I think as humans we're not very good about thinking about non-deterministic things. I think that's just a human trait. um and so how do you kind of like solve that? um I would argue that one way to solve it is basically observability and evals. Observability lets you see exactly what's going on inside the agent so you can understand it better. And evals lets you quantify how well the agent is doing. Are there areas where it's performing well or performing poorly? Like with evals, you can start to quantify that. Um, we have some tools in the space that again I'll talk about later. But just as one anecdote, uh, there's at a lot of there's a large financial institution which, like many companies, probably has an AI governance kind of like board that looks at all things that use AI, and you have to get approval from them before you ship it to production for end users. And a big part of that is because they want to understand kind of like, yeah, what's the like how likely is this AI thing to work? What's the risk associated with it? And we had one customer, one user of one of our platforms, Langsmith, which I'll talk about in a bit, which provides this observability and evals. And when they presented in front of this committee, or in front of this board, they got through in like record time. Like the meeting ended early, and normally meetings never end early for these types of things. But the reason was because like observability and evals exactly kind of like we didn't build it for these regulatory purposes. We built it to build better agents, but it turns out that building better agents, a big part of that is making them more likely to succeed, and not having these error cases and understanding these error cases. And that's exactly what this committee wanted to understand as well. So I think this is a good example of how even if you don't improve the agent, knowing how it works, knowing where it has failure modes, knowing why it fails is important for kind of like increasing the perceived kind of like probability of success. And so I mentioned this, but this is Langsmith. It provides this kind of like observability, this tracing, and then also this evaluation mode to measure how things are performing over time. And then the last thing I want to talk about is the cost if it's wrong. So right now, I would argue this has like an outsized effect in people's mind right now. Right now, when you see stories about AI on Twitter, they're for the most, or well, I'd actually be really curious, like what percentage of them are positive or negative. But I've definitely seen a lot of kind of like negative examples of AI messing up, and I think this captures a lot of headlines, and so I think it has a pretty like outsized effect in people's minds right now. And so how do you deal with this? And I think a lot of this comes back to the UI UX of the application you're building. So less actually on the agent itself and more on how users interact with it. So one thing you can do is you can make it easy to reverse. So I think code's a great example of this. So this is Replit agent. It's a coding agent. You can see here that when it suggests kind of like code to do, it shows this diff. This is very familiar for any kind of like software engineers. Code, generally you work on branches. You can roll back to previous commits. Sorry, code, you have commits. You can roll back to previous commits. You can roll back multiple. You can see kind of like what changed. And so this ability to like roll back lessens the impact if the agent is wrong. Like when I'm using Claude Code, I normally make sure that I check in my code, I commit my code, I then click off Claude Code, and if it messes the stuff up, I just revert it. It's pretty easy. Um, the other thing you can do is add more human in the loop. So coding is another great example of this. And so coding has a concept of basically PR reviews, right? So that's where you add a human in the loop, and you can see what the agent changed. I mean, PR reviews existed to see what humans changed, and so it was already kind of like a natural thing that's in there. And the idea is, it does this body of work, and then you add a human in the loop to basically look at it and approve it before it merges into master. Because if agent writes some code on a branch, it's fine. If it merges into master and deploys it automatically, that's less fine, right? So you add this human in the loop step to basically review it. And so yeah, there's different styles of this. You can basically interrupt. You can you can interrupt. You can ask for approval to like execute a tool. Like if you have a tool that runs a SQL query, you might want to like, you know, add kind of like add some step there. Now, what's interesting is like how do you balance this human in the loop with one of the things we talked about earlier, which is like letting things run for like a long period of time, or letting things do more, I should say. Because like basically if you add a human in the loop at every step, then the agent's not doing much each time and it's really annoying. And then each agent like run, you know, it doesn't have that kind of like high score in terms of like what it's able to do. So the key is basically figuring out places where you can let it run for a period of time, but it still has this human in the loop component before it kind of like gets merged in, quote unquote. And so if we think about some examples, I would argue that they fit like this bill of these three things. So uh, uh, so deep research. Deep research, you know, it runs for a long period of time. It's doing more work. But it's still basically this like first draft of something. It doesn't like, you know, publish the research report under your like name for everyone in the world to see. It doesn't send it to your boss. It just like it just has it there and then you can decide what to do with it. You can edit it, you can decide not to use it. It very much has this human in the loop. Same with Claude Code. We've talked about Claude Code a few times. But with Claude Code, you kick something off, it runs for a while, it creates like a PR, and then or creates a commit, and then you review it. Both of these I think have balanced this like have a human in the loop, but only have them in the loop at like a critical step, and before that, let it run for a long period of time, so it's doing a lot of work. I want to talk a little bit about some of the things that we're building in this space, and then I'll talk about some of the maybe more future directions that we see the space headed. So I've already mentioned a few things here. Um, One is LangGraph. So LangGraph is our agent orchestration framework. Um, a few two key kind of like pillars that we build it on. One is like controllability. So you should be able to define like both explicit and implicit workflows. And so this is like, you know, the deterministic or the non-deterministic workflows. And so represent things as graph. You have super kind of like fine-grained control. Each node and each edge here is nothing more than like raw code. It's just a Python function. So you can really you can call out to APIs, you can run arbitrary code, you can do whatever you want inside these. It's super flexible. The thing that we add in that we think is valuable is basically this agent runtime. And so that comes in with persistence. So this is like short-term memory, long-term memory, human in the loop functionality, durable execution, streaming, human on the loop things. And so this provides a lot of this stuff that you're going to need to build for agents out of the box. And a lot of this stuff is aimed at like the UX of agents. So like this persistence layer powers this human in the loop functionality. We talked about human in the loop earlier and how that's important for minimizing the cost of things being wrong. And we see that human in the loop's a huge part of building agents. And so LangGraph's kind of like really built with that in mind. Um, and maybe just kind of like backing up even more on kind of like the philosophy of LangGraph. LLMs are great. They take in some text, they output some text. We think LLMs are better when you combine them with external things. This is what RAG is. You do a retrieval step and then you do a generation step. We call this a chain. This is how LangChain company got its name, language chain. Uh, LLMs can do what is called as like tool calling. And so this doesn't actually call the tool, but it generates a payload for the tool. And so this came out, you know, 2020 mid 2023, and then widely supported in 2024. And what does this let you do? This lets you build this new kind of like non-deterministic thing where you run things in a loop, where you start, you generate a payload of a tool to call, you execute that tool, and you loop until you're done. And so that's kind of like a lot of the founding belief behind LangGraph is basically letting you move anywhere on that spectrum. So like combining these chains with these loops, and letting you move anywhere on that spectrum. In terms of the things that that LangGraph supports. I mentioned a few of these already, but like long-term and short-term memory are two parts of building agents that are pretty important. Short-term memory you can think of as like conversational memory. So if you're interacting with a chatbot, the list of messages is right there. But it can also get more complex. Like it can be a summary of the conversation. It can be kind of like other artifacts, like files that are uploaded. But it's all scoped within that like conversation, within that thread. Long-term memory, on the other hand, exists across threads. So if you have an agent that you want to learn from one conversation to the next, uh, long-term memory in some form is how you'd power it. Human in the loop we talked about. This here is I'll talk a little bit more about this later, but this is LangGraph Studio, which is basically like an IDE for building agents almost. You can't do the drag and drop stuff here, but you build the agent in code and then you interact with it here. What's the benefit of that? You can add like human in the loop kind of like interaction patterns where you can basically add starts and stops when it calls a certain tool or something like that, and you can mess around with this here, and then you can also build it into your own UI. Um, one of the things that one of the other things that we're building is LangGraph platform. So this is a deployment platform for agents. It's really good for like long running, bursty, or stateful kind of like applications. And so a lot of the tooling we build is for places where we see agents headed. We think that agents are going to be like more and more long running, more and more stateful. You look at like Claude Code, deep research. I'll talk about these later, but these all use some aspect of kind of like statefulness. A lot of them have access to a file system, for example, and then they're all long running. They'll run for like minutes and a lot of or hours even, and a lot of traditional web infrastructure isn't super built for that. I'm going to skip over that because that's boring. This is more exciting. This is LangGraph Studio. This is our visualization for agents. Even though you build agents in code, it's still really handy to see them visualize. Like that helps you kind of like understand what the agent's doing, the logic inside of it. When agents mess up, they generally mess up because there's the wrong kind of like logic in the agent in some form, and part of that has to do with the graph structure. And so being able to see that and debug that and visualize that is really helpful. I talked about LangSmith already, but just reiterating, LangSmith helps kind of like with debugging. You can see exactly what goes into the LLMs. I can't stress enough how important this is. Like when you're building agents, when agents mess up, they will mess up because of a call to the LLM. Why will the LLM mess up? Usually it messes up because you've passed bad information, incomplete information, too much information to the LLM. You need to be able to see what that is. And so LangSmith started by providing that, and then expanded into evals, because once you can debug one data point, you then want to basically measure performance across a bunch of data points, because you fix this one data point, you want to make sure no regressions happen, like it keeps on working in the future. And then once you go to production, there's a whole another problem of kind of like observability over agents in the wild, not just on a single data point, but over a lot. And this is something that we're pushing on a bunch right now. This is a pretty active area of development. Okay, I want to pivot a little bit and talk about deep agents. So this ties into some of the stuff that I talked about before. Namely, if you so and so actually, like I started thinking about this is a very new thing that we're talking about. We just released stuff for this in the past few weeks. A lot of the ideas for deep agents were like the earlier part of this presentation I gave at the AI Engineer Fair. That was like 2 months ago, and I started thinking more about like what made some of these agents successful. So like the examples I gave were like Claude Code, deep research. Manus is another one that's kind of like popped up as something that can run for a longer period of time and be successful. And so what makes like all of these successful? Because at the core, they're still running that loop of like calling tools in a loop. Like there's nothing the core algorithm's still the same. But if you just like naively give like an LLM some tools and ask it to run the loop, it's not going to run successfully for like 30 minutes or an hour. So why are these other agents able to? That's basically the question that I started thinking about. inspired by agents that are working on more general tasks. So Manus is pretty general purpose. Claude Code, a lot of people started saying, oh, Claude Code you can use for more than just coding. So that's kind of interesting. What makes it useful for general tasks? And then they're running over longer time horizons. And so okay, like general tasks, longer time horizons, that's interesting. What makes things good at that? Um, to maybe just make the longer time horizon things more concrete. This is an example of a benchmark of basically like how long of tasks can models do. And so you can see that measured in humans, like how long would it take a human to do it, and how long and can a model do it? And basically, um, you can see that the length of tasks that they can do is growing. So, what makes agents like this, like Claude Code and Manus and Deep Research is another example of this. Like, what makes agents like this good at doing that? Um, I would argue that there's a few things. Um, so I would argue that all of these agents have some aspect of planning. All of these agents are stateful. They offload context to a file system in some form. They like management of state is really important. They use subagents. This lets them go deep on particular areas. And then they also have like really detailed and extensive prompts. And this sounds basic, but I'll talk more about it. I think it's a key part. So maybe diving into all of these. So the the issue with agents trying to do longer time horizon tasks is they're often not kind of like cohesive over those longer time horizons. One thing that you can do to help agents be cohesive over longer time horizons is quote unquote planning. Like, why are humans cohesive over longer time horizons? Because we can plan. And so how do agents do this? There's a few different modes, but they all do some aspect of this. So Manus saves a to-do list to plan and then to repeat objectives and to help steer the agent. So they have a concept of a to-do list that they save as a file. Um, Claude Code, Deep Research, they do planning and then get user approval on that plan. So Claude Code, there's plan mode. When you turn it on, it will generate a plan. It will get user approval. Deep Research, it has a back and forth with you up front to try to get to basically figure out more of what you want to research, and that's basically its plan it's putting together. And then Open Deep Research is one of our implementations of Deep Research, and Anthropic multi-agents, they have an explicit planning step where they don't show the plan to the user, but they have a step where they generate a comprehensive plan. Claude Code by itself should also go here. This is actually pretty interesting. Claude Code has a to-do tool that actually does nothing. So it doesn't save it as a to-do list anywhere. It literally is just there so that the agent can call it, and then it's in the context window of the agent, so it remembers it. It's basically giving it kind of like a fake scratch pad to write things down. But all of these agents have some aspect of planning. All of these agents use the file system in some way to offload context. So Anthropic's multi-agent system, they have ways for subagents, which I'll talk about in a second, to basically write down notes as they're doing research that the main agent can see. Manus uses the file system to write down a to-do system. So it combines it with the previous planning thing to write down kind of like to-dos. It also uses the file system to read and write token-heavy context. So if you call an API, it might return like a massive JSON dump. And rather than just putting that in the context window of an agent, what Manus will do is they will put it in a file system and then ask the agent to kind of like manipulate that file system. Basically like read from that file system, write from that file system, do things there. And then another use of this file system is basically for long-term memories. So if you want information to persist between runs, you can use a file system or a virtual file system to do that. So that's an important thing as well. this file system doesn't have to be like a literal file system. It has to be some, or it can be some like quote unquote virtual file system. You're giving it like a scratch pad, essentially. It just so happens that LLMs are really good at working with file systems and working with CLIs. And so it's pretty natural to give it either an actual file system or like mock out tools to approximate a file system. A third thing that they all do is they use subagents. Um, and so some examples of this. You can you can use subagents to split context across multiple different agents. So what does this mean? This basically means that if I spin up a subagent to research X and another subagent to research Y, as they do their research, there's no need for them to know, and there's no need for the main agent to know about like all the search queries it does and like all the paths it goes down. All it needs is the final answer that it generates. So these subagents effectively create like this context isolation for a particular task, where they can do work that doesn't clog up the context window of the main agent, and they can just be very focused on it. Um, these things that the subagents do can basically be tasks that the main agent kind of like delegates. So this is probably the most common pattern. Is it's not like a swarm of agents all acting like independently and all in parallel. No, it's a main agent creating a task and then delegating it to a subagent and asking it to do it. And so it's really just like creating that clear context window. Um, but there are some cautionary tales. So Cognition has a blog post about like multi-agent systems. Um, and so oftentimes multi-agent systems can make conflicting decisions. And so the example in Cognition is that if you ask basically, if you try to split up like writing code and writing tests into two subagents, they might make some conflicting decisions about the API surface area or something. So oftentimes, one thing to help with this is to use subagents heavily for give them a lot of access to tools that can read content, but not as much access to tools that can write content. So if you're thinking about, so what does that mean? Like subagents are great researchers, but it might be really hard to have them write an essay in parallel. Like if I write a first section, and then Evan writes a second section, they could they could they could be not consistent, right? Like it's tough. But if I go do research on something and Evan goes and does research on something else, and then we have a boss that takes our research and writes it into a report, that's much more kind of like congruent and can be more consistent. So so one of the things that we did in our deep research example is basically do research the read operations in parallel with subagents, but then the write with a single agent. And then the last thing I want to call out is just prompting. I think there in some circles there's maybe this sentiment that like prompting is dead. Like models will get better, you'll never need prompting. If you look at the system prompts for all of these agents, they're like pretty complex. Like if you include tool descriptions, Claude Code system prompt plus tool descriptions are like 2,000 lines long. Like those are like pretty, beefy like prompts. And they make the models, right? Like if anyone should have short prompts, it should be them. Um, but the truth is that in order to do these complex tasks, like you need to impart into the model how you want them to do those complex tasks. And they're constantly updating this. So this is like a diff of the system prompt, and you can see that they change a bunch between versions. So they're constantly iterating on them. It's pretty important. And so kind of just like to summarize, to look at like a few different examples, Manus, Anthropic's deep research, our open deep research kind of like example, and Claude Code, they do all of these things. So Manus uses a file system for planning as well as for dumping context. Anthropic's deep research uses it to basically pass notes between subagents. Claude Code obviously uses the file system locally. Our Open Deep Research uses like a virtual file system. They all do planning. Claude Code has a plan mode and this like fake to dual calling. We give a think tool to our Open Deep Research. Anthropic's researcher has a plan that's saved. Manus uses a planning tool. They all use subagents for delegation, and they all have pretty complex prompts. And so if we combine all of these things, we get what we've been calling kind of like deep agents. We wrote a blog on it. It's basically still this core idea of just an LLM running in a loop, calling tools. What's the new idea? Good system prompt, a planning tool, a file system tool, and subagents tools, and then whatever other tools you want as well. And so the thesis basically is if you give them these things in addition to just the tools that you would naively give them for a task, they can do things over longer time horizons and with more accuracy. And so we have a GitHub repo called Deep Agents. This was a fun weekend thing that I worked on 3 or 4 weekends ago, and we've been investing more and more in ever since. So I definitely encourage you to check it out. We have some examples of both research and soon coding built on top of this. And so the last thing I want to wrap up with, and then I'll leave some time for questions, is how do we scale even more? So we've talked about these like deep agents. We've talked about this idea of, hey, how do I like going all the way back to like improving the probability, improving the value of right, and decreasing the probability of wrong. I've done all of that. Now what? How do I scale that even more? So we have this formula for determining kind of like the ROI of agents in the enterprise. Let's just multiply it by something. And so how do we do this? We do this with ambient agents. So this is another idea that we've been pushing a bunch. What are they? The basic idea is that ambient agents are agents that like run in the background, listening to events and acting on events. And that lets us multiply the impact that they have. So chat agents, when I interact with a chat agent, they're triggered by a human message. Ambient agents, they're triggered by events. This could be like an email coming in. This could be a Slack coming in. This could be anything that's happening. This lets us scale ourselves. So if I'm chatting with an agent, I can generally only chat with one agent at a time, maybe 2 if I'm getting fancy and have 2 open side by side. With ambient agents, because they're listening to events, there can be however many I want running around doing stuff. Chat agents, again, this gets back to the scaling, generally 1 at a time. Ambient agents kind of like unlimited. Latency requirements. Chat agents need to be fast. So yeah, if I'm chatting with an agent and it doesn't respond in like 5 seconds, I get bored. Ambient agents, because they're kicked off by events, can take a lot longer. If I have an ambient agent that's checking my email, I haven't checked my email in the past like 2 hours. Like it could be taking 2 hours to try to respond to an email for all I care. And so what does this let us do? This lets us do more complex operations. So if I'm chatting with an agent, it can generally just call an LLM and then respond. Maybe it can do like a single LLM call. But with these ambient agents that run in the background, they have more time to do things, so they can do more things. And so this is also where deep agents comes in again, because deep agents will take a lot longer to run. And so there's kind of like some interlocking or interleavingness between all of this. And then the last thing is so that we think about is like how do you interact with these agents? So chat agents clearly you interact with like in a chat UI. That's been the dominant form of interaction patterns with agents so far. Ambient agents is maybe like a little bit different. So I think there's a question mark about what the right UX for ambient agents is. And I want to call out that like ambient does not mean like fully autonomous. I think sometimes people hear ambient agents and they think, okay, like agents are going to go like run around in the background. I don't need a UI. Why do I need a UI at all? UIs are still important because ambient agents aren't fully autonomous. How would we want to interact with them? This gets back to like the human in the loop aspect. There's a few different ways we might want to interact with them. We might want to basically like approve or reject tool calls. We might want to edit the actions that they want to take. They might want to ask us questions. So we need to be able to answer their questions. And then there's also this concept of time travel, which is basically like if the agent runs for 100 steps, what if they mess up on step like 53 and I as a user want to go back to step 53, point them in the right direction, and then have them go from there. And so there's all these like human in the loop interaction patterns that are still really important even for these ambient agents. And so one idea of a UX that we like is this idea of like an agent inbox. So this is all kind of like interrupted agents. So agents that were going along their like merry way and then ran into some action that requires human approval or human editing or human feedback or something like that. And so that we call this agent inbox, and it's an open source UI. We're not claiming this is the best UI, but I think this is a really interesting space to explore. And so just to make this more concrete, I have an email assistant, or if you think about an email assistant, it's one that's listening to emails that come in. Those are the events. It can take like 5-10 minutes to respond. Like I don't check my email every 5-10 minutes. And I probably want, especially to start, I probably want to um still be in the loop. I probably want to know if it's scheduling, like maybe it can read my emails and maybe it can propose drafts, but at least to start, and I this is actually a very real thing because I do have an AI email assistant that I built. Like I'm still in the loop. Like no emails go out unless I press kind of like send, but it drafts all the drafts for me. And same with like calendar invites and stuff like that. And so this is open source. It's called Executive AI Assistant. You can probably find it on our GitHub online.